We're now going to discuss inverse functions, and we're going to look at the example of f of x equals x squared initially, okay? So what does an inverse function for this mean? Well, let's look at a graph first. So the graph of this function looks approximately like this. And for instance, if you take x equals to 2, then evaluating here, well, will put you at square root of 2. So what does the inverse function do? Well, he's supposed to do exactly the opposite. So we can represent this in a different way. So I can say here that 2 is sent by this function f to square root of 2. Now the inverse function, as I said, wants to do the exact opposite, which would be to send this back. And this is true for any other input of f and output of f. And here, of course, we could view this as f inverse starting from the y-axis and going down here to the x-axis. So this is what f inverse wants to do. This is a peculiar interpretation because here we can view this as the x-axis for f. And by this, I mean the input for f, right? So we could call that axis whatever we want, u-axis or t-axis or something. But x is what we're used to here. And this would then be the x-axis for f inverse. But of course, if we call this the x-axis, then it's natural to call this the y-axis. And then we would have to think of the y's as the input for f inverse, which can be a bit awkward. So we try to avoid that. But the thing is, so if I now really think of this as the x-axis, I label this as the x-axis, and I label this as the y-axis, well, here we have the graph of f inverse, although we would have to put our heads to the side and then kind of think of it as a mirror image because we're used to the graphs lying the other way. But here is a program that kind of allows us to visualize this process. I'll draw the B here. So this is the square root function. Here's the x-axis, here's the y-axis. Imagine now that I call this the axis and this the y-axis. Oh my goodness, the axes are in the wrong place. So I slide here to reverse their positions, and then we see the inverse of the square root function, which we know should be x squared. And he looks, well, exactly like this. So the next question we're going to look at is how to invert f algebraically. Well, then let's start by writing y equals f of x, okay? And then let's insert the formula for f of x. So here we have y equals square root of x. And so when I wanted to invert visually, the first thing I did was to swap the roles of x and y. And by this, I just mean relabeling, renaming. So this means I now have this relation, okay? So now I'm really looking at this as the x-axis. I'm calling this the x-axis. And then I solve for x, or solve for y. And I mean, for different functions, this can look, I mean, this process will be different. But here, it's just squaring each side. And here, the implication looks like this. And then I'm done, because here we have a formula for f inverse where we'll view, or where we've labeled its input by x. So next, we're going to notice the following. So not all functions can be inverted. And let's here take an example, which is kind of peculiar, really. We'll get back to that. So the example would be y, or let's perhaps write f of x equals x squared. He's not invertible. Okay, so let's explain this. So if you draw his graph, it looks more or less like this. Well, it doesn't go under the x-axis here, but you know. And now, for instance, if I do 2 here, then, well, not completely to scale, then we would read off the value 4 here. So again, we would have 2 being sent to something by this f, in this case 4. And now, what would the inverse do? Well, the inverse would stand at 4 and think, okay, so who is f sending to 4? I want to send him back. Should I send him to 2, or should I send him to -2 here, right? Because f also sends -2 to 4. So here we are having a bit of a conundrum. Should f inverse here send to this or to this? We have a choice. And once we have a choice, everything collapses, okay? We cannot invert a function that sends multiple x values to the same y value. We need to have one and only one origin, so one and only one input that corresponds to each output. And functions having this property are called one-to-one functions. So one-to-one functions are exactly those functions that you can invert. Okay, so let's just write the definition of a one-to-one function here. So definition, f is called one-to-one if for each y in its range there exists exactly one x in the domain of f such that f of x is equal to y. So that's one way of defining it. Another way of defining it, which gives exactly the same concept, is that we can write it as a proposition, since this is the definition. Proposition f is one-to-one if and only if fx1 equal to fx2 implies x1 is equal to x2. So notice that this statement here is exactly the same as this statement here. Why is that? Well, if you have two x values, they give you the same y value. Well, then the x values had to be the same. So no two different x values can give you the same y value. I'll leave it as an exercise for you to write up a proof for that. Visually, we interpret this, or we can think of this as like a horizontal line criteria. So let's put a horizontal line here. So if the function intersects a horizontal line more than once, it's not one-to-one. So here we intersect twice. What does that mean? Well, it means that there are two x values that correspond to this y value. So the horizontal line criteria describes visually what one-to-oneness means, and it means exactly that for each y value, there can be at most one x value. And finally, here we can write the definition of an inverse function. So if f is one-to-one, then we define f inverse by following. So f inverse of x gives you y if and only if x is equal to f of y, right? So I'm wondering here, okay, what value should I assign to this x here? Who should f inverse send x to? Well, f inverse should send x to the y, which is such that f sends y to x. So we can write it like this. So x is being sent to y by f inverse if and only if y is being sent back to x. Exactly the drawing we have up here, except I switched the roles of f inverse and f, which is just about switching the labels from here, between here and here. And now finally, well, let's try to see what happens algebraically when we try to invert something which cannot be inverted. How do we detect problem? So let's do it here. Let's try to invert algebraically f equals to x squared. So now we're going to do exactly the same procedure as when we inverted algebraically the square root of x, except, well, for this function. So first I write y equals to f of x. This is basically saying that I'm using x to label the x-axis for f and y to label its outputs. I put in the formula for f of x like this, and then I swap the names of x and y, so I get x equals to y squared. And then I solve it, but if x is equal to y squared, this means that y can be equal to square root of x, or y is equal to minus square root of x here. Oops, here I have a choice, and this means I cannot invert, because it means that for this specific x, there are two choices basically for the y it can correspond to, which is exactly what we saw up here. So how do I solve it? Well, if we go back to this thing here, notice that if I started with square root of x and inverted, I'm not exactly getting x squared, am I? Because there's nothing here. No. Notice, so when I'm inverting, the domain of my function becomes the range of my inverse. And similarly, the range of my function becomes the domain of my inverse. So when I inverted the square root of x, since the domain, or since the range of square root of x is only positive numbers, then I'm getting x squared as the inverse, but restricted to the positive axis. And that's a general thing, because if we now start here, so let's start here with x squared instead, then you see, and let me slide it over here, then you see that, well, this guy doesn't satisfy the horizontal line criteria, so it cannot be inverted. But if I restrict his domain like this, then this guy satisfies the horizontal line criteria and can be inverted. Similarly, if I would restrict the domain like this guy satisfies the horizontal line criteria and can be inverted. And whose inverse is this? Minus x squared. So algebraically, notice here. Here I can restrict this guy, let's say, so my x squared. So I restrict this domain to positive x's. When I swap the role of x and y, this restriction is translated into restriction like this. But this means that this is not possible because this gives you negative y's. So this means we can choose this. So we know that of these two possibilities, this is the one that we're going to choose. So restricting x squared to positive x's makes it invertible because then we know what choice to make. And correspondingly, if I restrict to negative x values, I would get here a restriction on to negative y values, and that would be my choice to make. So restrictions in the domain of f tells you something about the range of the inverse. And notice here, if you try to invert something that cannot be inverted, then algebraically, you'll notice this the second you're given a choice that you don't have enough information to make, basically. And that's that.